Окей, but probably, but, но там запись идет, да? Ага. So, okay, since this is recorded and there might be some people in the audience, or not in the audience, but those who want to follow the course. So let me switch to English. So so is it fine with you? So switching to English? Yeah. Okay. So okay. So let me say first of all that since the situation is unstable and the format of the class so far it's kind of offline, but with possible use of Zoom as we do now. However, I don't know what's going to happen next week or the week after the next one. So please write me an email to say Skoltech address or Gmail address, just saying that you are kind of interested. And so I'll be able to send you a notification. And also just to be sure what's going to happen next week and after that. And also I'll probably create a web page so you'll be able to follow the updates there. Okay, so our class is on vertex operator algebras. And so the theory is rather well developed by now. So it started from physics and then kind of went to mathematics with the aid of representation theory and algebra and so on. But also it has wide range of applications in geometry, combinatorics, well, quantum field theory and so on. So we'll do mostly the algebraic part, but of course there will be some geometry behind, and maybe we'll discuss some geometric applications. We'll see. But anyway, so we'll start with some basics and then go to some more sophisticated issues. So so the class will be once a week, and then we'll have lectures, and also you'll have homeworks and short problems once each week. So I'll upload the problems, the homeworks, and the problems to the web page, and you will be asked to somehow send me the solutions back to by the email. Okay. So also we'll have a midterm somewhere in the middle of the semester, and also because of the situation, which is very unstable, please follow the updates on the page. Okay, so any questions so far? Okay. Yeah. Yeah, so far it does not exist, but I'll create it, and then after you send me your emails, I'll send you back the link. Okay. Okay, so today, so let me just make a short, brief introduction. So the main ingredient of a vertex separated algebra is a field. So we know that an algebra is an algebraic structure where you have elements and you have some operations. So for associative algebra, this is a product. For Lie algebras, this is a bracket. So there are many various options. But for vertex separated algebras, the situation is a bit more complicated in the sense that you have fields. And this is, well, in physics, you would consider it as a separate object. In mathematics, you'd rather write it as, say, y of z, which is a series in z, say a and z to the n. Well, you may want to consider y of z just as I said, a solid object, and then work with it, or you can consider the Fourier expansion and try to develop the theory with the use of this an. And then, of course, you have to define what are those guys. And the vertex separated algebra, this is a collection of fields. And of course, so there should be some operation on the fields or some operations on its Fourier components. Well, we are going to study, but just for you to have a kind of understanding what kind of structure we're going to consider. So this is these objects with some operations. Okay, so what's important here is that we have a sequence of objects. These are ANs, and this explains why infinite dimensional algebras show up in the story, because so in order to define one such a guy, you need already infinite number of features on the right. So let us start with a very basic example. So this is the so-called Heisenberg algebra. And boson fermion correspondence. But so this is probably the first instance where these vertex separators show up. But probably most of you have seen these constructions. So could you please raise your hand if you are familiar with such a construction? Okay. So also, could you please ask people, or I can ask if they hear me. So in the Zoom listeners, could you please let me know if you're familiar with boson fermion correspondence?
Yes.
I heard something.
So are there still somebody? So,
yes.
No. Okay, and who is the person? Okay, okay, and who else is there? Okay, okay, okay. So then let me do the following. So I'll outline the basic, the main parts of the construction, and then we'll see how deep we want to learn on the details. So let me consider first the Heisenberg algebra itself. So let H be the Heisenberg algebra. So what's that? So it's spanned by the elements H, K, K and Z, and one extra element C, such that the commutator, this Heisenberg Lie algebra, and the commutator of HK, HL is delta K plus L 0 times K and C. So it means that we either have 0 or some multiple of the element C, and this C is central, meaning that HKC is 0. By the way, let's ask Irina, is it visible what's written here? Is it good enough?
It is, but the camera just kind of wobbles here and there, and
okay.
I would prefer it if it was stable.
Oops. Okay, so this is the Heisenberg Lie algebra, and so we can clearly see it's infinite-dimensional, but the commutation relations are very simple, and actually, we can somehow realize this algebra in a very explicit way. Namely, there is something called the Fock module. So it's defined by a number lambda lambda is just a complex number. And as a vector space, this is a module over the Heisenberg algebra. So H module. And so as a vector space, phi lambda does not depend on lambda. So it's isomorphic to the polynomial ring in infinite number of variables. So lambda is not here. And so we have to define what is the action of our generators. So let's say that HK acts as d over dx minus k for k k greater than 0, and h minus k acts as k times xk for k greater than 0, and h0 acts by multiplication by lambda, and finally C acts as I did. So let's see if it works. So could you please check if the operator defined in this way satisfy this relation? Yeah, so just to make sure that the coefficient k is here and this is the correct coefficient.
It's because you should check that HK and HL is different, not opposite numbers.
Yes. They commute? Yes. Right.
And if K and L in sum give 0, it means that
yes.
commutator is commutator partial derivative and
multiplication. Yes, you're absolutely right. So if we take, say, hk and h minus k, and say k is positive, then so this corresponds to the commutator of d over dxk, and k xk, right? And then this commutator is exactly k. And since we know that C acts just as an identity, so this is actually what we want. Okay. So now, how should I use it? If I go there. Sorry, some problems? Okay, so I'll slowly move further. Meanwhile, so let us put a following lemma saying that pi lambda is an irreducible
Поверните камеру, пожалуйста.
H module. So can you explain why?
Can you please rotate the camera?
Okay. Okay. So so the proof works indeed as follows. So assume that V from pi lambda is a submodule. Then such that V is non-zero, then there exists a vector, non-trivial vector in V, and V is actually a polynomial P of x1, x2, and so on. And if we take, so if x1 to k1, or rather L1, well, let me write it as follows. If xk1, xks is a non-trivial monomial in V, in P, then H K1 HKS applied to V is equal to some constant, non-zero constant times 1. Okay, and then also if we apply the polynomial algebra in h minus 1, h minus 2, and so on to 1, then we get the whole P lambda. So let me add a remark. Saying that the remark says that the span of actually several remarks in one. So span of h minus 1, h minus 2, and so on. This is commutative subalgebra in H, and also H1, H2, and so on. So these are commutative subalgebras. And also important thing is that H0, H is 0. Yeah, so we have central element C, but also the H not commutes with everything. Okay, and so like this, and one more remark. So vector 1 in pi lambda is usually denoted by lambda in cat notations. Okay. So this is the remark, and so we've seen that h k lambda is 0 for k positive, and h not lambda is lambda times lambda for 0th part, and then if we apply all the remaining operators, then we get the whole space. Okay, so this is why so pi lambda is called the sometimes Fock module or highest weight module, but these are the crucial properties. Okay, so let us somehow study some, well, numerical facts. So for that, let me write that pi lambda equals to the direct sum over integers, non-negative integers, pi lambda comma n. So where pi lambda comma n is the vector space spanned by monomials of the form x k1 x ks with k1 plus kx equals n. Okay, so this n is a non-negative integer. So in particular, so for example, pi lambda 0 is just c times lambda. So we don't apply any operators, and this is just a one-dimensional vector space. And the question is, so what's the so can we say something about the dimension of pi lambda n? So please raise your hand if you know what's the dimension of pi lambda n. So Zhenya, can you say what's that? Right. So this is the number of such monomials, but is there some way to describe it in a more concrete terms? But why? So. So can somebody?
Yes, it's the number C of n plus 1.
We can write boxes and where the balls and balls. I don't know formulate it.
Yeah, but you're absolutely right. So we can actually, we even don't have to work too hard here, yes, because so what's written here? So we need, since these are commutative variables axis, yeah, so we can assume that k1 is greater or equal than k2, greater or equal than ks, and their sum should be n. And this is exactly the Young diagrams with n boxes, yeah, just by definition. So diagrams with n boxes. Okay, and so, well, there's no simple formula for such a number, but what we can do is we can introduce the generating function. So the character, or rather Q dimension, of pi lambda is by definition the sum over n, q to the n, and here the dimension of pi lambda n. So you see, this is a series in Q. And again, let me ask you, please raise your hand if you know the answer for such a thing. So Angelina, what's that?
Your function.
It's 1 by
Mhm. But okay, let's see what's that. Yeah, so if we expand 1 over 1 minus q, so what we get is 1 plus q squared plus so on, right? So in particular, this would mean that the coefficient in front q squared is 1, right? Yeah, but it's too small, yeah, because so we have 2 can be expressed as 2 or 1 plus 1, yeah? So this q squared is not enough, right? So what should we add?
We should find another picture of all powers of
That's it. And so there's a short annotation saying that this is q infinity. So please say in voice if you want to discuss this equality in more details.
what it means to discuss.
Just do we want to prove it or we don't? Okay, so this is the kind of q dimension. So we can't compute the dimension of the space because it's infinite dimensional, but we can do at least such a computation. And so one more thing to say. So we've shown that this module is irreducible, and we've computed its dimension. So let us put one more lemma. So assume that V is an H module such that there exists a vector V in V with the following properties that H 0 V is lambda V, H positive V is 0, and H let me write it like C of H minus 1, H minus 2, and so on. V is the whole thing. So then V is isomorphic to pi lambda. Okay. So can we prove it? So once again, please raise your hand if you can prove it. Okay, then maybe you can say a few words.
Construct homomorphism from lambda
Mhm.
which put
So lambda maps to V, yes.
yes,
Okay, and
then ну и дальше продолжается h минус
yes, yes, and h minus I1, h minus ik, V of lambda maps to h minus I1 minus ikv. Okay.
соответственно. Теперь надо воспользоваться необходимостью. Сейчас нам нужно, что у нас v является mod v. So we know that mod v is factor model of
Indeed. So phi is a surjection. You're right. Right. And
phi have not kernel because phi lambda is reduced.
right. Right. Okay. So that's it. Good. So probably that's all I wanted to say about this bosonic part so far. Yes. So let's go to the fermionic part. And so how does it work? So we want, so this is called the bosonic picture. And now we want to consider the fermionic part. So in other words, we want to get a slightly different realization of the same module, and for that we would use fermions, so skew commutative operators instead of these commutative types. So so let V be the direct sum of so just a vector space with basis Vi, I from Z. Okay, and yeah, maybe already here I can show you the first example of a vertex operator, just to show you what are the objects we want to study. So this is the, say, sum hn z to minus n minus 1 n over z. So you can see here the modes, the hns
Turn the camera,
are
please.
either the elements of the Lie algebra, the Heisenberg algebra, or they can be considered as operators acting on the Fock space. But totally, this guy is a field. You can imagine this a field acting on phi. Yeah. Okay. So let's go to the fermionic part. So we have this vector space, and our basis is Vi. I is an arbitrary integer, and then So we want to consider to construct Vertex space, but since this V is infinite dimensional, it makes sense to consider kind of infinite Vertex space. It's called semi-infinite, and actually there are several types. So not to use the same symbol for different objects. So we fix M from Z, and we consider, well, maybe before that. So let's use this object for a large thing, and let me define it. So this large thing is going to be span of the expressions of the following form: vi0, which vi so 1 or minus 1. What should be the convention? Let me use minus 1. Vi minus 2 and so on. Okay, so this is the span of such expressions, and what's important is that I0 is greater than I minus 1, greater than I minus 2, and so on. Well, the numbers are decreasing, but we also insist on the condition that I minus k minus 1 equals to I minus k minus 1 for k large enough. Okay, and so an example of such a vector is provided by the so-called highest weight vector M, which is Vm minus 1, minus 2, and so on. So this is the product where you start with some fixed M and then you go down. And in general, we define the Fm to be the span of vectors vi0, vi minus 1, so on, such that I minus k equals to M minus k for k large enough. Okay, so this means that our vector coincides with this M for large enough numbers. Okay, and then clearly remark the semi-infinite Vertex space is isomorphic to the direct sum over all M Fm. So this is the so-called charge decomposition.
Last question.
Absolutely.
So for what purposes we demand that for k like house, this condition is false. So for the space to have countable basis, or that's other.
So you mean this condition? So you see, we need an action of some operators on this space, and in order these operators to be well defined, we need such a condition. So if we allow arbitrary numbers here, then the definition we are going to give doesn't work. Yeah. So it's important that so we can draw a picture. So say this is 0, minus 1, minus 2, minus 3. So this is just V with such numbers. And then we say that from some point, they are all occupied. And here there might be some gaps. And this tail is important for our definition. Okay. So that's fine. And now let's do one more thing. So let's define for v I0, which vi minus 1, which so on. Let the degree, I don't know, let me say that this is W, the degree of W, and this is a vector from Fm, is defined as the sum over k greater or equal than 0, I minus k minus m minus k. So so this is an infinite sum, but actually the number of non-zero terms is finite, right? Because we have a condition that I minus k is actually m minus k for k large enough. And so this is the degree. And you see here the condition on the tail is already crucial. Otherwise,
Please turn
there's no
the
way to
camera.
define it. Okay. So, and
Пожалуйста,
let us,
поверните камеру.
consider the degree decomposition, direct sum overall n greater or equal than 0. Yeah, by the way, is it clear that this number is non-negative? So the numbers I are decreasing. So I mean, yes, but why then? Why is it implies that this number is non-negative?
You can consider some number where it's 0,
Mhm.
and when we go left, it's number I minus k increase question, I think, 719.
Right.
And minus k will increase. Well,
Right. So indeed, so we have I0 greater than I minus 1, greater than I minus 2, so on, greater than I minus k. And then here we have numbers m minus 1, m minus 2, and here m minus k. And we may assume that this is an equality for k large enough. And then clearly, since these guys increase by 1 to the left, these guys increase by at least 1. So yeah.
So the only reason why considering infinite sequences instead of finite is to get the great
So you see, the important thing is that for this k should exist, yes, for which I minus k is m minus k, but it's not fixed. Yeah, I mean, for different Verge products, this number can be different. Yeah, so we ask for such an equality, but this equality can happen at any place.
Yes, they're considered stabilizing sequences. So finite sequences plus gradient by the last step.
Finite sequences plus where it stabilizes. Yes, but this place where it stabilizes is not fixed. Yeah, so it can happen at any place. Okay, so well, now this Fm is a direct sum Fm n, where Fm n is the span of
Поверните, пожалуйста, камеру.
degree n Verge products. Okay, and we can ask for what's the dimension of Fmn. And again, I want to ask you, please raise your hand if you know what's the dimension of Fmn. What do you mean finite dimensional case?
So it's like a dimension of a state of the V or finite dimension of vector space or.
Well, I mean, this space is finite dimensional, yes? So the degree n.
Yes, so it's just a number of this phenomenal coefficients.
Why?
Just because phenomenal, maybe the sum is phenomenal. Yes, the sum is 2 in power of dimensional space.
But what space do you mean? So I mean, dimension of what space?
So yes, yes, the question says V is not finite dimensional.
Yes, V is infinite dimensional. Yeah. So we fixed infinite dimensional V, and we also fixed this charge M. And then inside of the given charge subspace, we consider those vectors which have degree n exactly. And we ask for the dimension of this degree n space.
So it's dimension. The number of coefficients of the dimension of M.
Say again, the dimension, like binomial coefficient of what? What should I put upstairs?
The dimension of Fm.
But you see, it's infinite dimensional,
Yes.
because so what we are saying here, that at some place we have the tail, yes, the compact tail, and after this we have here whatever we want. Yeah, so in principle there are infinitely many things of this sort. Yeah, probably you know, but may just one second. I want to ask. So anybody else? Can anybody else answer? Sveta, do you know what should be?
It's dimensional is a number of partitions of M.
Yeah. Sveta, do you know?
Нас слышно?
So we need. So what we need is these. You see, these numbers. Well, it's not 0, but m minus k. Yeah. Or what do you want to do? Why 0? What is 0? These ones, yeah. Okay. Yes. So from some point they're 0. Yes, you're right. Well, actually, what we want to fix is just this sum. Yeah. So so this is the degree. Yeah. Why? What is this rectangle? But so you see the number of terms here is not fixed. Yeah, so in principle, we are not saying how many non-zero terms we want here. So this is an arbitrary number in principle. So the only thing we ask for is that the sum of these numbers should be fixed. Yes, should be n. That's true. That's true. But actually, this is what Svet already said to us. Yes, so in the sense that we only care about these differences. Yes, and we don't care about the m itself, right? But so we are very close to the answer. So what should it be? Yes. Yeah, that's right. So this dimension is actually nothing but is equal to the, well, P of n. This is the number of partitions of n. Yeah, and the reason is actually very. Oh. Okay, who did say it? Okay, very good. By the way, how many people in chat in Zoom do we have now? 3 people. Okay, so let me actually repeat for those who didn't attend from the first minute. So please send me an email to my Skoltech address, just saying that you are kind of participating in the course, so I can have your email to somehow update you with the further changes. Okay, so and the reason is kind of very concrete. So we have such a partition, n is, say, lambda1 plus lambda2 plus so on, and lambda1 greater or equal than lambda2, so on. Then we can somehow attach to such a partition vector v m plus lambda1, verge v m plus lambda2 minus 1, and so on. So you can see that since this is a partition and it's finite, then from some place have a tail effect configuration. And well, by the very definition, the degree is equal to lambda1 plus lambda2 plus lambda3 plus so on. So it's exactly.
So each number of ordered partitions or
well, anyway, the partition is just such a collection. So a partition of n is a collection of lambdas which are non-increasing, such that their sum is. So in particular, we derive the Q dimension of our Fm, which is again 1 over Q infinity, which is a shorthand notation for 1 over product 1 minus Q to the right. That's it. Very good. So this is the answer. And so the remark is that if the q dimensions of Fm equals to q dimension of y lambda, and this is not a coincidence in the sense that we can endow the Fm with the action of the Heisenberg algebra. So the goal is to make Fm into an H module. Okay. Good. So how to define the operators? So let lambda k from z be an operator on V such that lambda k of VA is VA minus k. Okay. So then we induce lambda k to Fm. So in what way can somebody suggest? So how should we define the operator lambda k on Fn? So starting this lambda k on V itself. Say again? So, well, we want to say to apply lambda k to some Vi0, Vi minus 1, Vi minus 2. So what's that? The sum over n greater than 0, and we put Vi minus n minus k, keeping all other vectors untouched, right? So this is the formula, but can you explain why does it make sense? So there are infinite number of terms in principle, and in our space we have only finite number, finite sums. So is it contradiction or there's some nice feature here? Okay, maybe once before you tell us, please raise your hand if you know why this is a finite sum. Yes, Zhenya, can you explain?
Because at some point every number will start appearing in the sequence of bits. So when we apply it to some number after with k plus the operator,
Right. So indeed, so since this k is fixed, right? So this comes from this number. this means that I minus n minus k, so there exists a, so the remark, the sum is finite, because there exists an S such that, well, let me write in words, there exists, because our wedge product contains tail, so which is of the form v sum s, v s minus 1, v s minus 2, and so on. Yes, and if we take this n such that the subtraction of k does not move out of this tail, then such a vector would reappear once again. Yes, so we assume that if well, the usual rule saying that VA wedge VB equals to minus VB wedge VA. Okay. So we assume that if we somehow change the order, then the product would somehow give us extra minus. And therefore, VA wedge VA is 0. Good. And of course, so for all but finite number of terms here would get repeating vectors. Okay. So now these are our vectors, and let us denote by Rm of lambda k, the action of lambda k on f. So this action. Very good. So these are our operators, and now let's see. So let's try to make a computation here.
Сейчас что-то слышно из зума через колонки?
Да, слышно?
Да, слышно? We can hear you.
Спасибо.
So any question?
No.
Okay. Okay. So we know that what is the commutator of lambda k and lambda L?
0.
Yes, that's right. So this is 0, and this is still true that if we take Rm of lambda k and Rm of lambda L, this is still 0.
K is not. K and L can't be.
First of all, this is a very good issue. Yes. So let me add a remark here. Actually, maybe even there. So the action of lambda 0 on Fm is not defined by
Not in
our
the camera,
formula.
please.
Sorry?
I was to in the camera.
So the action of lambda 0 is not defined. Can you explain why?
Because there will be infinite sum.
Yeah.
It doesn't converge.
So it does not work, absolutely. So we can just by hands define it by saying that Rm of lambda 0 is just m times identity. So we'll get back here, but assume first of all that k and l are different. So the question is it still 0?
Can we use for every? Can we group so each operator acts on each part of the sequence. So we can just use the action of the usual operator and just take it from.
So you think that it's still true, right? Or what?
No.
Maybe because there are problems with something and
Okay, then since at least this is not clear for everybody, Sasha, you probably know, right? Okay, so then let's make one computation. So let's do R0 lambda 1, R0 lambda minus 1, commutator applied to 0. So can you tell me what's that? Sorry? Said I'm sorry. I don't hear. Lambda minus 1 increase the index. Yeah. Yeah, that's right. So actually this is 0 because so if we apply first R0 of lambda minus 1, then this would increase. So our 0 is V0, V minus 1, V minus 2, and so on. And then when we apply lambda minus 1, we increase the index by 1. And there is no way to increase all these guys, but we can only increase this V0. So R of R0 of lambda 0 applied to 0 is V1, VH V minus 1, VH V minus 2, so on. And if we get back with R0, oops, of lambda 1, R0 of lambda minus 1, and it's going to be back 0, and in opposite direction, so it gives 0 right away. Yeah. So the question is, the answer is that it's non-zero. Yeah, it is not in general, right? So now the question, so let us put the following proposition, asking for this commutator. So do you have an answer? So at least what Sveta suggested is that it should be something like delta k plus L 0. So if k plus L is non-zero, this should vanish. But otherwise, what should we get?
We should add k.
Yes. So any suggestions why this should be true?
Maybe straightforward computation.
So it's just a number of customers. So which are
Well, so there are some, there should be some cancellations. Yes, I mean, there's the difference of the product in one direction and another direction.
You can easily see that, for example,
Yes. Okay. So, so if we apply Rm lambda k, Rm lambda L applied to the vacuum M, then we can indeed see that it's 0. But why? 0 or k?
it is key when they are obvious, because you can ладно, можно сдвинуть один из этих вершин на К.
Yeah, so have M, M minus 1, M minus 2, so on. And then, so if we apply L first, yes, L should be, yes, so assume that K is minus L. Okay, let's assume that this is positive, or like this, or no, vice versa, yeah, like this. To the left, it increases, yes.
So that can shift one vertex from the first car.
That's true.
Car
True. So we have here up to M minus K plus 1. And so this Rm of lambda minus K shifts it to the left. Yes. And then we can get shifted back.
And if we after that consider the action of lambda k, we can see that there is only one vector from this whole combination, which we can on which we can notion vector. And it's not only one, vertex.
Mhm. Mhm.
And this vertex, it is exactly the same, which we. В общем, это та же самая вершина, которую мы только что переставили.
Ага.
Надо ее обратно переставить, и все получится. А вот если мы пробуем что-то другое переставить,
Mhm.
ну, очевидно, да.
Yes, but this, so you are saying that there are exactly, so this should be k times delta k plus L0, right? Times m. So you are saying that if k equals minus L, then you have the terms which produce you this k, but what about other terms? So you might somehow act, so take some such a vector, move somewhere here, and then take another vector, move somewhere else. Is it possible
It's possible, but
or not?
it's a commutate. If we shift two different vertices, it is not.
But probably we cannot in this situation, yes, because so actually, as you said, so we take first such a vector, for example, yes, move it here, and then the second guy would like to move backwards by the same number of steps. Yes, so far. Yeah, yeah. Yes. So if k is minus L, then clearly this is indeed k. And if k is not L, k is not minus L, then how do we proceed?
The first step is the same,
Mhm.
and when we lambda a,
Mhm.
and when we consider lambda k, we see x by 0
Mhm.
because it can shift chart. Если мы можем двигать обратно, это меньше.
So okay, so let us at least we've fixed at least this is a conjecture so far, and Sasha more or less explained in a way how this can be computed. Yeah, but what's important actually is that, let me say one thing, that you want so we have operators E, I, J. So these are say matrix units acting on V. So ij are arbitrary integers. So we have this eij, so as usual, and then our lambda k is nothing but the sum over all I plus k. So I from Z. Yeah, so I just want to say that Eij applied to Vj is Vi. Okay. So this is the action of Eij on V, on our initial infinite-dimensional vector space. And the lambda k, these are operators on our initial V, they are just such sums. Yes. So Ei, I plus k, because so they move Va to Va minus k. And now we can, in a similar fashion we did before, so we can define, so we, maybe I write over there. So we can induce the operators to Rm of Eij. So these are induced operators on Fm. So they're induced by the same Leibniz formula.
Can you please move the desk just a little below?
Below. Like this?
Yes.
Does it work now? And what we want to compute actually is the commutator of Rm of lambda k and Rm of lambda L, which is simply the sum Rm of Ei I plus k with Rm Ej j plus k. So after all, what we need is to compute this commutator. Such commutators. Okay, so I'll probably more or less stop now. But what I want to say is that so this will be left for you as an exercise for your homework. But just what was the goal? Yeah, so we found some operators which produce the same relations, commutator relations, as we expect from the Heisenberg algebra. So we'll get back to this next time. But so I'm done. So any questions?
Thank you.
Thank you.
Welcome. So once again, please write to me so I know your emails and